My name is Hartej and my topic is neural network zoo, and my focus is on variational autoencoders. Coming to the presentation agenda, first I'm going to speak about the neural networks and then explore neural network zoo web page, and then talk a little about the generative models, and then introduce variational autoencoders and the theoretical foundations such as Bayes and latent space, is which are used in the variational autoencoders, and the variational approach which the VAEs use, and then talk a little on about the architecture wise, like the encoder and the decoder, and then the functions in the various encoders such as loss functions or maximization algo function, and then talk about the dynamic training dynamics and the challenges faced during the training, and then about the applications uh, of the various autoencoders. Coming to the introduction to the neural networks are computational models as inspired by human brain, and like for an input space, if you feed it to a neuron and which has an activation function, this is the sigma function which is for a basic neuron, it adds all the weights, and then give it to an activation function. It could be a real or a sigmoid function, and then it but like for every neural network, there are several key elements such as neurons and the layers, the input layer, the hidden layer, and the hidden layers are in the middle, and the input layer are on the outside. And the inputs have the weights and biases. And coming to the neural networks web page, it categorizes the neural networks into several categories, 6 categories to be exact. And those are feed-forward neural network, perceptron, and feed-forward and deep feed-forward come into that category. And then they talk about the recurrent neural networks such as RNN, LSTM, and GRU, and then they talk about the autoencoders such as AE and autoencoders and variational autoencoders, etc. There are neural networks which have the capability of say restoring the memory, and then comes the deep learning innovative methods such as convolutional neural network. It can be GAN, which have a generator and then uh, adversarial network which tackle each other, and there are differentiable neural computer and neural Turing machine and attention networks defined in this website. Coming to the generative models, there are many generative models. We are going to talk about the autoencoders first. The autoencoder are setting an encoder and a decoder as a neural network, and then to learn the best encoding and decoding scheme using an iterative optimization. And so, with a given input space, yes, the main agenda is to reduce the dimension of the space. Like if the dimensions are in 28 cross 28 dimension, we reduce it to a 28-bit space, and then we try to reduce it to a single point. And then using this point, we generate the given input with the minimum loss as possible. Encoder. And coming to the variational autoencoders, instead of reducing it to a single point or a single vector, we use Gaussian distribution function. They have every distribution function has a mean value and say sigma value, which estimate the uh, point in the latent space. And so it is not a single dimension or a single vector space, but it is rather a distributed function in this scenario. And a variational autoencoder can be defined as being an autoencoder whose training is regularized to avoid overfitting and ensure that the latent space has good properties that enable generative properties. They have to ensure that the latent space has a good generative process also. Coming to the variational autoencoders, they have two main parts, encoder and decoder. The encoder essentially compresses the input into a lower dimensional latent space, and the decoder reconstructs the output from this latent space. In the variational VAEs, extend this concept by introducing a probabilistic fish. That is the Gauss distributed function. Coming to the theoretical foundations, all the encoders are based on the neural networks. Basically, are based on the Bayes theorem, which is defined as the probability of latent variable z, given that x is already in the already given input is given. For a given input, the probability of z is what we actually calculate. Okay, the latent variable assumption. The assumption is that there exists some representation of z that, if known, would make a generation of x in the other data points. A variational approach to this autoencoder, is a variational post-it. Instead of computing the probability of z given x directly, use an approximation function q z by x, the encoder, which is tractable and parameterized by phi. And we also have a KL divergence variable, which is the difference between the true and the variational post here, which is measured using KL divergence. It is suppose in a given local minima and a local maxima, if VAE estimates that this point is at this particular location, and we instead of calculating the distance between the location, we use this divergence method, which is not actually a point-to-point distance by say, but it is a function on a whole. Coming to the architecture, we like VAEs have encoder. This part of the network maps the input data to a probabilistic distribution in the latent space. Yes, so this is the probability distribution we were talking about. And it basically learns the parameters, the mean and the variance parameters of the every distribution function has the mean and the variance parameter. Instead of pointing it to a latent space, putting it on a single point, we use a mean and variance function. And these are the assumed of a Gaussian. These are assumed for a Gaussian distributed representation. And the decoder. And coming to the decoder samples a point from the latent space. Like they'll pick up a point from the latent space and reconstruct them. And but this process is similar to the similar in the autoencoders. Coming to the encoder PAE, the encoder network is basically built of a deep neural network. The encoder is typically a DNN or a multi-layer perceptron network, which is basically it will convert the latent space and the input into distributed function on a latent space, and the output parameters are basically value, which is mu, and the variance, which is sigma power 2. So this is the average of the term and how much distance. For a normal distributed function, these two values represent the average and how far is that function from how far is the point from the mean value. Coming to the loss function, so the objective of the VAE is to minimize the elbow function. Elbow is derived from the log of the likelihood of the data, and this means how likely is the data compared to the if you get an output, how the probability of the data is given as the elbow function. This can be generated using the reconstruct the input data. The loss function is basically calculated by reconstruction of input data and subtracted with the KL divergence. Okay, the first term reconstruction loss, the expectation of the log likelihood of the data given the latent variable. This term encourages the decoder to accurately reconstruct the original data. Coming to the second term, it acts as a regularizer. It forces the distribution function to be as close to as close to the as near to the output as possible. And to train a VAE, we need to tweak and improve it based on its performance using a method called stochastic gradient descent. But there's a problem with that. The encoder's output is random, so it's not a producing a range. It's not a fixed point. It is randomly generated, so it is very tricky to handle. And so for this problem, the variational autoencoders come up with a solution and called as reparameterization and meterization trick, which is the which is to basically generate a sample. The reparameterization layer solves this by reorganizing the randomness of the layer. Instead of directly using the random output of the encoder, it adds a known and a fixed randomness epsilon to the deterministic part of the deterministic part, mean and the variance. Like mean and variance are fixed, but we add epsilon to this function so that we can fix the randomness. The formula z equals to mu plus sigma into epsilon allows the model to maintain. To building a variational autoencoder, we just have to initialize this function, and like every model has an encoder and a decoder and a total loss to keep a track, and these are the metrics. Basically, we can import this whole thing from the Keras and neural network model library or TensorFlow library and just use it directly. We don't have to worry so much about what it actually has in terms of building the model from scratch. Training dynamics and challenges. So like the problem with you can face several problems during training, such as scale divergence vanishing problem. In some cases, the scale term the loss might collapse to zero, making the model ignore the latency. This is very common in VAs because the scale divergence collapses to zero. It doesn't, and it can the neural network cannot generate new things, but it will keep on generating the same old thing, and this will be a problem during training. And mode collapse can occur when the model generates a limited variety of output, and like the our latent space is strictly inside a little circle which you cannot go out of. So that's why making it harder for the function to generate new outputs which are very outside the latent space but still inside, but still makes sense. Coming to the applications, the variational autoencoders can be used in semi-supervised learning, and the VAEs can be extended to semi-supervised learning scenarios where only a subset of data is labeled. Disentangled representation research in VAs include learning disentangled representation where different latent variables capture different independent factors of the variation in the data. We generally use the VAs for data creation and for creating new data similar to what it is they were trained on. Like if you train on data of cats, you can generate a new image of cat which didn't exist before. Compressing the data into a more manageable forms, and then we can also use it for anomaly detection, identify data points that don't fit in the general patterns of the dataset. And the research in VA is including learning disentangled representation where different latent space capture the independent factors of the various data. Thank you.